3 points, short introduction. Then I will present the WILIAM energy module and some of the most interesting details. So I picked some of the details which I think are relevant. And finally, and then some preliminary results that should also serve to demonstrate how the model works internally, so that you can see with data what I first show you in charts, basically. So let's start with the why. Why is energy important? Well, that's a very general question. Obviously, energy is important for every area in human life that you can think of. We need it to fulfill basic needs and reach a decent level of well-being in general. It's in food production, as Margaret just explained before, in fertilizers. It's in the diesel that we need to run our tractors. It's in healthcare when we run machines. It's in transportation. It helps keeping up this complex web of interactions that we've built up that forms our modern society. It's essential for communication, for production. In short, there's pretty much nothing that isn't enabled by energy. We created all this energy surplus to we harness this energy surplus by harnessing fossil fuels to build up this society, this complex economy that we have today. And it enabled us great progress and advancement. But obviously, the other side of the medal is that basically this is the greenhouse gas emissions and over time. And you see the yellow part is emissions from energy. So 3/4 of emissions are from the energy sector, which is still to a large or to the biggest share dependent on fossil fuels. And this is an important one very important reason why obviously we have to look at it in detail in integrated assessment models. And also there's a lot of dynamic in the system. Since I was born, the greenhouse gas emissions from energy have increased by 70%. Like I was right about here. And there's even more dynamic in the system. I mean, lately there's a certain degree of decoupling that we see. So relative decoupling, which means that GDP grows faster than greenhouse gas emissions grow. In some countries, even absolute decoupling. So GDP grows, but emissions reduce. So this is what proponents of green growth are really happy about, and they want to see absolute decoupling in all countries. But anyway, what I want to say is there's important changes that are happening right now in the system, and to a certain extent, they also go back to crazy price developments. For example, if you look at PV, which in just a couple of years reduced its price from $400 to megawatt to 70, and this is already old data. I mean, now it's even much lower in Austria, at least. Like PV has already overtook onshore wind as the cheapest form of electricity generation. And I think AEA recently titled that the PV transition, it's already so cheap that it is now you don't need to support it anymore. It will change the system by itself. And we see similar developments and learning curve developments also for batteries, for example. So we have a lot of changes that are in the system, and a lot of changes that are also apparent and that will appear in the near future that we need to model in detail in order to capture the dynamics that they will invoke in the whole system. So we can't ignore this dynamics. So let's briefly run. So what do we do in WILIAM in the energy module? Well, the major goal of the energy module is to model these consistent annual energy balances, taking into account all these developments that I just was talking about, in order to provide the relevant feedback variables for the rest of the model. Most prominently, obviously, the greenhouse gas emissions that Noelia just explained, that are one of the major inputs to the climate submodule. What they mean with annual energy balances, I suppose that most of you are familiar with energy balances. In general, an energy balance shows the flow of energy from primary energy via transformation or energy conversion to final energy consumption. And it's a consistent framework in which this is done. Maybe some of you have seen Sankey diagrams like this one here by Eurostat. By the way, very great source. You can check out Sankey diagrams or energy flow diagrams of all EU countries over the years. What you can see there is you have primary production or imports. So this is primary energy. And this energy, like oil or gas, for example, or biomass, and this energy is transformed, for example, to electricity or district heat, or just from one oil product like crude oil to another oil product like diesel or benzene. And then it's either exported or used domestically for final consumption. And this is what we actually want. So we want to use, for example, the electricity in households or in industry or in transport. Same goes for the fuels, of course. And all this whole conversion chain is displayed in energy balances. And this is what we're modeling. And this is also one of the major design principles in our energy model, that we are consistent with the International Energy Agency energy balances. And another principle when designing the module was that we have a good representation, especially of those technologies that are likely to play an increasingly important role in sustainable scenarios, like renewables, obviously, and storage, demand-side management, hydrogen, and such things, while also taking into account biophysical limitations that we foresee via feedback loops. For example, land use for PV, we just heard about that from Marga. Also biomass use for energy, for example, but also material requirements, fuel scarcities, material. You will hear more about that in the next lecture then by Ole. We'll model fossil fuel consumption with markets and stocks. But also there's limitations to renewable power sources. So let me run you through an overview of the energy module. What you see here is like the arrows in green are the inputs and the red arrows are the outputs. The yellow ones are policies. So I will run you through the most important elements of this simplified representation. So up here you have the economic demand in dollars. So this is what we get from the economy module. So it's basically the economic output by sector. And the first step in our energy module is to convert this economic demand in US dollar into energy demand, so kilowatt hours, and the different final energy commodities. So we do this with a mixed bottom-up and top-down approach. For example, transports are modeled very detailed bottom-up, while other sectors, industry especially, is modeled top-down with energy intensities. And for buildings, we are still work in progress, but we also want to model this bottom-up. So the output of this end-use submodule is the final energy demand. And this final energy demand is the major input to the transformation module, where we actually, this is the heart of the energy module, where we model these annual energy balances. So it's a representation of the whole transformation chain from primary to final energy. And And at one point, I will go into detail on that. We also need to allocate electricity and district heat demand to the different transformation technologies that we have in the model. So the output of this energy transformation module is primary energy, obviously, which translates into greenhouse gas emissions. This goes to Noelia. And the fossil fuel demand also goes to the materials module, where we have where we model the fossil fuel market on a global level and so on. This will come later in the next lecture. In order to be able to model this energy transformation, we also need to take into account the energy capacities that are existing. So we need to know what's the power plant stock and CHP stock and heat plant stock that we actually have available, and how does it develop? How much phases out each year? How much is built new? How does it develop? And this creates obviously a demand for investment, for both material investment and monetary investment. And it's also subject to constraints. For example, wind or PV potentials are also not limitless, or hydropower potentials, for example, uranium availability, but also capacities are just not limitless. And one result is also the energy. One thing that we do model that many integrated assessment models do not is the energy return on energy invested. So with the typical example is also always oil, that where, for example, the energy return on energy invested is high. Which is good, high ratio of energy that you need to invest to get out 1 unit, one unit of energy, and this ratio worsens over time. But it's the same for renewables. Currently, this is only an indicator, although we want to implement a feedback also on energy end use. And the last important submodule is the variability management, because we all know that intermittent renewable power generation, especially by wind and PV, is challenging the electricity grid. Yet we have an integrated assessment model that works on an annual time scale, and certainly we don't have grids. We don't represent grids in the system, for example, and we have only annual time resolution. Yet we had to find a way of modeling this sub-annual timescale effects in these annual energy balances, because if you have a high share of PV and wind, you're likely to see some curtailment during times of high production. But then obviously there's also technology that helps to absorb these energy quantities, like power to heat, or maybe flexible electrolyzers, batteries, this sort of stuff. So we have our own submodule where we basically emulate dispatch model results via statistical correlations on our annual energy balances. So let's go a bit more into detail into the transformation submodule. So usually the energy flow will go, as I explained in the beginning, from primary energy, and then it's refined and transformed, and it goes to final energy. When calculating in the flow of calculation, it's the other way around. So we start off with final energy demand. This is what we get from the end use submodule. We take into account transmission losses, storage losses, sector energy on consumption, or electricity that is used for flexibility processes, to end up with the transformation output demand that our power plants or that our energy system needs to supply. So this transformation output demand is allocated to the different transformation technologies. We'll go into detail for this allocation because, I mean, we look most prominently, we have electricity and heat, and this is allocated to 30 different production technologies. And obviously, you need to think of some logic of how this allocation takes place, what are the priorities, and so on. So this gives us the required transformation input. And if you add regeneration losses, you end up with the primary energy demand. So it's quite straightforward, although in detail it's, as always, a little bit more tricky. For example, here the allocation in the model, we have heat and electricity that we allocate. And we have three types of transformation technologies, which are CHPs that produce heat and power, heat plants that produce only heat, and with heat I mean district heat, by the way, and power plants that produce only electricity. So the way we approached this was that we implemented a stepwise allocation. So first we allocate the total heat demand to the CHP and heat plant technologies. And then we deduct the electricity that comes from the CHPs from the total electricity demand and allocate the remaining electricity demand to the 20 different power plant technologies. And what is important here is what's the priority for allocation. So and this allocation in general influences a lot the short-term dynamic of the power system. And we use the operation expenditures as a signal to prioritize one technology above another. And so in these operating expenditures, we also take advantage that we have endogenized fuel prices for fossil fuels, at least in a model. And we also have policy assumptions, like especially the CO2 price, which is very important. So this is our allocation priority. And you can also set it to exogenous, if you wish, or to a mix of endogenous and exogenous models, endogenous and exogenous signals, as you prefer. So this is for the short-term dynamics, this allocation. With regard to the long-term dynamic, which is probably even more relevant in an integrated assessment model, this more depends on the actual capacity stock of transformation processes, POTRA transformation processes. So obviously, each year you have a certain fraction of the capacity that is phased out because it has reached the end of life. And this amount of capacity needs to be replaced by some other technology. So here again, we also have the issue with CHPs that can produce electricity and heat. So we also have this stepwise approach, but also you have to decide on a signal that gives you on a signal for the priorities. So in this case, for example, we are using the levelized cost of electricity as a signal. Although in reality, this is not how it usually really works out. Oftentimes, because else if levelized cost of electricity would be the only decision criteria of which power plant type is being built, then we wouldn't see nuclear in the system, right? So it's to a certain extent, it's a very political decision also. So it's also possible to set this signal to exogenous and say, let's give, for example, let's build only renewables for the phased out capacity. And they are also, they can also be subject to, there's also biophysical limitations that can hit in as there with regard, for example, how much hydropower capacity is available in your specific region, and this sort of limits that we also implemented. So let me run you through the very brief through the third focus submodule that I want to go into detail, which is the variability management submodule, as I already said. The reason of this is to modulate the sub-annual timescale effect on annual energy balances with reasonable computational cost. And so we did more than 3 million dispatch model simulations with energy plan, and we created statistical correlations from the results, which we use to estimate the curtailment of wind and PV based on the current energy system setup in the model. So what we basically do is we emulate dispatch model effects in WILIAM. And what is important inputs? So there can also be flexibility options in the power system. For example, power to heat can help to absorb more electricity from intermittent renewable generation. Then we have one very important factor is the electric vehicle fleet and the fraction of this electric vehicle fleet that is available for vehicle to grid or for smart charging, meaning that you can that you allow some flexibility to charge your car when you have a renewable generation surplus, for example. Then there's stationary batteries, there's electrolyzers, demand side management. So these are variables that are taken into account in the variability management submodule, and that can be activated in WILIAM with a switch, basically. So enough of the theory. Let's show you some results, or at least here some preliminary results. So note that this is not really a consistent scenario yet. But now what I will do, I will explain you these results here, which is kind of the base scenario where nothing much really happens, and then change something in the model, and we'll show you the changes along these dimensions. So we have what you can see here is the sorry. Here we go. So you see you have these 6 charts. You see the different energy commodities, primary energy commodities that are being used in the system. There's a large fraction of fossils. You have the world GDP. You have the greenhouse gas emissions. You have the estimated oil price in the system, and you have the renewable share of electricity and the total primary energy consumption. What is already interesting here is that you can see that around 2040, sorry, we reach very high levels of oil prices, and in the same year we see that this has a dampening effect on the world GDP and also on the greenhouse gas emissions. So this is already an observation of peak oil in the base scenario. So let's change something. How does this work in general? So we have this huge scenario parameter file. This is only one kind of tab out of many. And we change some of the inputs. Like in this case, we give higher priorities to renewable energy technologies in all regions for capacity expansion, I mean. And we increase the amount of electricity that is being produced by introducing 5% of synthetic fuels for liquids and gases. So let's do that and see what happens. So first thing you can observe quickly is that down here in yellow PV and blue wind, you see the renewable share is increasing dramatically because we gave priority to renewables. And you can also see this here, that now we have almost 75% of electricity being produced by renewables. What is also important is that I'm not sure if you looked at the axis before, but so this is the this is the energy. Sorry, this is the transformation output by fuel. So this means the for electricity production. You can see that the total amount is about 25% higher. So we, for 5% of synthetic fuels, we're now using 25% more electricity. It is quite significant. However, we see that renewables work. We have lower greenhouse gas emissions. This is the gray line, and we also can reach a higher GDP because also you see that the peak oil is a bit delayed. So we reach higher GDP in total, and our total primary energy demand is also reduced. So let's change something. I told you, like in this scenario, we still act like all renewable power sources here are non-intermittent and perfectly dispatchable. So this is not realistic. So what we do is we switch in this variability effect that I was explaining before. So there's a simple switch that you set from 0 to 1, and you run the simulation again. And what you can see first is, well, that with such high shares of renewables, we actually do see a high share of curtailment. So this curtailment, I'm not sure if everybody is familiar with the term. This means that wind or PV are shut down because we have oversupply in certain hours. And this reduces the total, the renewables share of the overall system. And you can also see the yellow line, it reduces the GDP that is achievable, and it increases slightly the greenhouse gas emissions. Okay, this is what happens. So this is only one side of the medal, though. I did not switch on the flexibility processes that we also do have in the model. So let's do that. It's a switch. And what we can see if we turn on these options, that's the dark blue line. We can introduce the, oh, I just see now that I have a laser pointer here. The dark blue line, that it reduces curtailment and it increases the share of renewables that we can see in the system. And we can see here in the greenhouse gas emissions again also that the dark blue line is a little bit lower. And over here, the achievable GDP is higher again. So this is what happens here. However, there's one thing we did not touch at all for now, and this is actually the thing that everybody intuitively thinks that we need to do. We need to introduce behavioral changes and reduce consumption. So because we see up here that we still have relatively high levels of greenhouse gas emissions, right? 55 gigatons. This is still very high, certainly not sustainable or Paris compatible. So okay, let's reduce consumption in one sector, for example. As I mentioned, we have a relatively detailed transport submodule. So let's do two things. Let's do a modal shift of plus 20% of the person transport is shifted from individual transport to public transport, like train and bus. And from the remaining individual transport or car transport, let's change the transport the technology from internal combustion to electric vehicles, right? So the transport model works with is able to represent the modal share, the transport mode, the share and the change of this modal share, and also different transport technologies. So what happens, we would expect that now the emissions must go drastically down, right? Because we do this, we know that transport is about 30–40% of energy consumption, and we reduce this dramatically. So, but this is what happens. So you see the green line is transport, and we look at our greenhouse gas emissions, and we see they didn't really decrease, they even increased. So why? What's going on here? We have, if we look at GDP, we see that the GDP level we are able to achieve is much higher. And here you see that the oil prices that are there are much lower. So what we can see here is typical strong rebound effect of Jevons paradox, right? So we are less constrained, the economy is less constrained, so these efficiency gains are not translated into reduced greenhouse gas emissions, but instead into increased economic activity. And this is one typical example why it's so important to look at these issues in an integrated way, right? Because if I would look only at an energy model without the feedback from materials and economy, I would be missing a critical part of the picture. So briefly, what other we have a lot of other variables in the model that I don't have time to go into detail now, but one of them is, for example, energy investments, which we calculate endogenously, both in monetary terms. Although in monetary terms, this is not yet fully linked back to the investment matrix. This is ongoing work. But also in material terms, or in energy return on energy investment terms. I just briefly touched on that we also need to take into consideration the energy needed to produce new energy. We have still some work to do as well. As I said, like the scenarios the cases that I just showed you are not yet a consistent scenario, so this is still work in progress. We still haven't finished the building energy part. We haven't the EROI feedback present into final energy consumption, and probably one of the most important ongoing strands of work is that we haven't linked the investments to the investment matrix, and we also haven't linked the energy sector output to the A matrix of the IO model, which is something that we still plan to do. Well, preliminary conclusions before we come to the discussion. In general, I would say the WILIAM energy module is able to represent complex dynamics within WILIAM quite well, and it delivers the right feedback variables to the rest of the module. The model mechanics yield plausible results. One key conclusion is certainly that while the energy policies do play a really crucial role in tackling climate change, it's not sufficient to look only at the energy sector with regard to policies. As I just showed you, they must be complemented by policies in other sectors like land use and especially economy. And integrated tools such as WILIAM are a very good way to capture these complex dynamics. So with this, I think I'm almost in time, and we have time for some questions.
Lukas. Thanks a lot. Okay, so we have a few questions on the chat.
Oh yes, a second. Are there any retroactions regarding population and welfare? Is this for me? Are there
I think it's after. It's because so one question is because households save money and spend in other goods. So I think it's about one of the results that you show.
Does the energy module consider? I start with the lowest one first. Does the energy module consider resource limits globally and regionally? That's an easy question to answer because Ole is going to answer this question in the next lecture. So there's a whole thing about it, but short answer is yes. did you also model policies that might help to mitigate this rebound effect? Well, as I said, it's in this rebound effect would need to be tackled in the economy module to a large extent. I think efficiency is something that we can model in the energy module, but this rebound effect could, for example, be tackled in the economy module by reducing the propensity to consume. I mean, Simona, you're the expert on that, but that's sufficiency, basically a sufficiency policy that you can introduce in household consumption, right?
Yeah, I think so. And okay. Okay, there is a question about sector distribution of energy consumption.
Has a harmonization been made between the sectoral distribution of energy consumption and the NACE sectoral distribution in standard GDP statistics? Well, this probably refers to the A matrix, right? So this harmonization, well, ideally, and this is the idea is to have consistency between monetary flows and physical flows throughout the model. So that means, you know, in the economy module, we have an input-output model, and there you have monetary flows from one sector to another, like intermediary flows, and then to final consumption. And we made a big effort to make sure that the energy technologies we have represented in the economy match the energy transformation technologies we have in the energy module. So, for example, there is electricity from PV sector in the model, and there's an electricity from wind power sector in the economic module, and electricity from coal, for example. And then the idea is that when everything is linked, for example, electricity from coal, this economic sector will need very different input factors than electricity from PV. For example, if PV grows and coal declines, this means that you have more demand for electronic products from China, let's say, and less demand for national coal mining from the national sector. So ideally, when everything is linked and the A matrix is dynamized, we will see this effect, yes. But for now, this is still ongoing works because we ran into some troubles with regionalization and data, which is not always so straightforward. But we have come quite a long way, and I'm confident that we will continue working on this as well.
So, and Lucas, there are two nice questions. One is about what determines the energy intensity and how the price of renewable energy is modeled.
Mm-hmm.
The other one is about the volatility of prices, especially oil prices, if it is an assumption, and so how we
Okay. The second one on the volatility of oil prices, this is again a very easy one because this is going to be answered by Ole in detail in the next lecture. With regard to the first one, the energy intensity, well, for the industry sectors, we have historical energy intensities. So let's say kilowatt electricity per dollar output, and we let them evolve, and you can change how they evolve. So you can say what we can do in the policy, we can model a shift, for example, to electrification. And we can do this by sector, so that we can model in the, I don't know, food and agriculture sector, that it will consume less gas and more electricity for, I don't know, buying whatever. But this is relatively careful parameter settings that are needed there, I would say. And we do plan to model some sectors bottom up in the future, which is especially the iron and steel sector, which is likely to go to play a key role in in the decarbonization, right? Because it's a relatively large amount of greenhouse gas emissions coming from the iron and steel sector. And they are a major coal consumer for process-related coal consumer as well. And there's potential to replace coal by hydrogen there, for example. If there is a sudden, I see there's already a thread there. Mavi is answering. Very nice. Okay. If there's a sudden switch to renewable energy consumption, does this increase the cost price of renewable energy and have a negative impact on GDP? This would actually more be a question that I would pass on to the economic module. I'm not sure, Simone, when the economic model, probably tomorrow.
Yeah, no, it's on Friday, and we will explain also the link between the energy and the economy in details. And
okay.
so, of course, some effect on the price there will be, since there is an increase in investment and there is an increase in cost. And we will discuss on Friday a bit more clearly this interlinkage between the two modules.
The same is probably true. There's already this answer that Mavi was giving, because households save money and spend it on other goods. This is kind of the essential question in the production function, right?
Yeah, I mean, this is really the issue about rebound here. So, of course, if you're able to save money for energy consumption, I think this is the referring to, then, of course, consumers can spend more in other goods, and so activated a sort of rebound effect. This is the way in which we model it. And so at least on the macroeconomic level, let's say, there was something that Inigo was explaining on Friday. Okay,
right.
So I think we are running out of time. It's not your fault, Lukas, but we know that this day is intense. And so thanks a lot. It was really clear.